Okay. Hello, everybody. Thank you for coming for the Learning Lab 14. Today, I'm going to be talking about the third part in clustering models applied to the energy sector. Today, I'm going to have a guest presenter, Ninoska Amundaray, and it's going to be co-hosted by me, Daniel, and David. So just to introduce everybody, oh, it's not working. So Ninoska, she's a master's student, candidate at the University of Calgary, and it's also a member from CRUZ. And she's one of the specialists that we have in machine learning and data science. So she's going to be doing a very nice presentation today. So it's going to be co-hosted by me. Oh, sorry, Ninoska, would you like to present yourself a little bit?
Okay, well, yes, I think you say it all. So I'm just right now like a master's degree with CRUZ at the University of Calgary and an interest in machine learning applications.
Okay, thank you. So the co-host today is going to be me, Marcelo Guarida. I'm a data scientist and with a PhD in geophysics and head of the CRUZ Data Science Initiative. So Daniel Tread, Daniel, would like to present yourself?
Yeah, I'm an associate professor at the Department of Geoscience at the University of Calgary and collaborating with this project.
Okay, thank you. David?
Hello, I'm David Emery. I'm an incoming PhD student, but I also have 34 years experience in industry, predominantly on geophysics services aimed towards interpretation.
Okay, thank you. So it's time for a little bit of self-promotion in here. So this is the CRUZ Data Science Initiative. That's the one that's providing you the learning labs that you're presenting today. And also, as part of the CRUZ Data Science Initiative, we are part of the CRUZ, that's a consortium at the University of Calgary, where we do data science projects, can be consulting or projects for sponsors that are mostly to the geoscience focus, but also with other type of data. And we do projects that are academic and also industry-based projects. We also provide some training in programming languages that could be simple, not simple, introductory or advanced training in R, Python, and MATLAB, as well as applications in machine learning or even how to create applications. You can also go to the CRUZ Data Science Initiative part. That's the tab research link in the CRUZ website, cruz.org. And you can see all the information from the learning labs in the past. So now I'm going to just pass to Ninoska, and she's going to be starting the presentation. Ninoska, you are muted. I don't know if you're talking.
I'm trying to unmute myself.
Okay.
Okay, thank you. So as Marcelo mentioned, today we're going to be looking at a little project that we did with Professor Trad within the class of geomachine learning applications to geoscience. And this is just basically we wanted to apply clustering models to a velocity analysis portion within a seismic processing. So it is important to notice that in seismic velocity, there is a big component of velocity analysis. So that would be the peaking. And basically what you want to obtain in those cases is just a reliable velocity function that helps you to obtain the best stack of the signals. Therefore, you will able to enhance the signals in a region in those cases and get a horizon continuity. So if we notice here, we got different gathers, and those gathers, if we notice, depending where we're seeing on the top velocity panel. So depending on the velocity that we're trying to kind of go more flattened. And that will change depending how it's going to be the depth of the horizon of the event. So basically you want to maximize a velocity that helps you to correct the majority of those gathers and to get the best of your seismic. This velocity analysis relies heavily in the correction of the parabolic events associated with the seismic ray path traveling. So if we note here, we have basically 4 events, and we're noticing here basically the distance. So we have that variable event that's the travel time. And then if we take basically correct those events, taking basically the inverse of the velocity, or basically the slope of the curve of those, we get the velocity. So they plot it here between 1, 2, and 4, although it's the y-axis seems to be inverted. It's just like this one corresponds to this one corresponds to this, and this one corresponds to this, and so on. And these values of velocity are also related to this four point. This 4 point corresponds to the measure where the signal coherence is just like the highest, because you're able to correct the majority of those seismic traces. So we wanted to maximize and find basically how to, using a semblance plot, how to take that trend. Now a little bit of the disclaimer. So we try to take some of our workflow in reference to another paper. So there's a lot of people who's been working with clustering and semblance plot. So far, one of the papers that we took as a reference was a work by Smith in 2017. But since they don't exactly explain all the work process that they did, we basically just took it as a reference and then trying to adjust based on our case. So we divided our workflow in a part of the input, then a pre-processing stage, and then a machine learning application. So on the input part, we import the shot gathers and assembling panel that all was generated in seismic unit. And to generate the semblance against seismic unit, if we notice these red points against where are gonna be the biggest coherence of the events, or like kind of candidates to select or correct your events. So the semblance basically is just taking the SPs, the shot record, then you apply a constant NML correction, then you sum all of them and square them, and then divide those, but the same NML correct the gather, square, and then sum along the axis. And basically that's kind of like a iterative process, and they will get you like a different kind of candidate supplement that will help you to correct your gather. But as we notice, we kind of see different trends, and then we will have many candidates to form or to correct our seismic gather. And that's what we're trying to tackle in the pre-processing stage. So in the pre-processing stage, if we think about, well, if those red points it's gonna be the points where it's gonna be the biggest coherency, or you can correct the majority of your gather, why don't we take this and create an sparse matrix with 1s and 0s that will give us the information from the ones that pass, that will be like the red points, and let's say the blue ones are the ones that don't pass like initial filter. That is true, but if we notice, we could do that. But if we notice, we could have many of them. So we could probably define a train over here, but then we define a train over here, which it doesn't necessarily make sense for a geophysicist perspective, a geological perspective, that doesn't make sense. So for that, we're trying to do like a secondary classification, and then we're going to explain more. And basically what we did is just trying to refine that kind of trend from the semblance and update our matrix. So and of course this matrix, it's not entirely related to this, but if we notice, if we do a further classification, it's just get like, you get more restricted the points that you want to use as a cluster, at least as a candidate to correct your gathers. Now for the machine learning applications, first of all, we define a clustering algorithm. We have tried with k-means, and we're now moving forward to another ones with DBSCAN. But the clustering algorithm is basically after taking the semblance, after passing everything on the filter in the pre-processing, you will have some points that will pass those that filter. So the cluster basically is just trying to associate whichever is just close to them, depending on which method they're basing, if it's density based or if it's distance. They try to group all those data points and create those cluster centers. And then taking those cluster centers, you could create a velocity function. So here in the paper, they pretty much compare that guided velocity basically from a guided velocity from the semblance provided by an interpreter versus the one for the new velocity is just the machine learning application. And if you notice, at some point you can see like a similar trend, but the values that we're able to pick with this velocity, they're supposed to correct the majority of the gathers is just different. So when they did the NML correction in their case, and if they compare like the semblance out of peak with the machine learning, they claim at least, and you can see here that in some of the horizons, you can see like a better continuity of the events. So they suggest that maybe using like this machine learning algorithm could help to improve basically your final stacking gather. And this is some kind of like the reference. So now we're just gonna move to the code, and we're gonna explain more what we did and more like apply to our case. So here as we noticing, sorry, let me close this one. Okay. So in our case, we generate basically all the shots we generating using the Marmousse model that we get to see here. And using that Marmousse model, we generate the shot gathers and the semblance. It is important that for like the input parameter, you want to know some knowledge about your model velocity, or not maybe your model velocity, but you want to know at least have some information about basically where it's going to span the velocity, like let's say a maximum and a minimum. And you can actually, if you don't have a very good idea about that, you can start changing and see what adapts better for your case. So basically here we just import the libraries in this case, and then the libraries for the clusters. Now, as I was saying, like everything was generated here in Linux, and this type of variables is just coming from Linux to generate the semblance. So here we have basically the sampling in time, and this is the sampling time and the sampling in velocity. So taking those values that we already knew from Linux, we're kind of like read the semblance file that in our case, because it's coming from Linux, it's just in a bin file, and we reshape that one. Here you can pretty much just find the shape of the semblance and define the velocity. So this is why we're telling you the velocity axis, the time axis. This is just for resemble your data, and the velocity axis is just what is going to be like the maximum and the minimum value of the semblance panel. So that's kind of information you want to know. And if you don't know, you could just simply do by trial and error and see whether that's better. Now we're just basically plotting all the semblance. And if you notice, this is where we're talking about the minimum and maximum. So if I change this, let's say this velocity, the semblance is just gonna span in the velocity axis. So this kind of information, if you have some knowledge, prior knowledge, is just very good, and it will do just better. It will run smoothly in your case. So as we notice in our semblance, we do have kind of like an upper tail, and then we have like some kind of like trend here that will tell us that that's could be some points of like representative velocity to correct our gathers. And then, well, we say, well, let's do the initial classification just to find in the threshold. So if we notice the semblance goes between 0 to 1, so 1 will be the one with just the biggest coherency of the signal. So we will say, well, if we take something that's close to 0.1, maybe that will be the candidates that you want to use for your cluster.
Ninoska.
Yeah.
Could I just ask one?
Yeah.
Why do we have this upper tail?
Well, basically, it always happens. It's some kind of like an artifact that could happen in your data. So And I'm going to talk about that. This is such an artifact that you just want to get rid of it.
Okay.
And yeah, sorry.
Yeah, I can add something there, Ninoska.
Mhm.
What happening in the shallow is that you don't have many traces with energy, right? Because it's so in the shallow you basically have as you calculate the move out, you only have a very few traces alive, and because
Right.
of that, the semblance transform of that, it becomes basically energy everywhere for all velocities because it's poorly resolved. So it's just blurring is the effect of the lack of resolution in the very shallow. So yeah, it's very typical for semblance to have that.
Thank you, Daniel. Very well explanation. Um, okay, so now we understand that that's something that happens continuously in semblance. So that means that we want to try to get rid of those kind of points. But again, like we said, well, let's define and just use this threshold. In this case, I basically we can play with this threshold with, let's say, whatever happens between 0.821, it's initial classification to pass to become a cluster. So if we do that, we notice here like we kind of lost some kind of the points that actually will be more representative to fits of the velocity, but we still have the upper tail. Let's say, well, let's be a little tougher with that threshold, and what you would happen to notice is basically that only past the tail. So using our such a very hard boundary for the threshold, it's not gonna be useful for really a very good cluster to correct your gallery. If you notice here, I just try to change another one. Again, it's always gonna pass this one because it's just closer to the one. And you're gonna have just really small candidates to form and to actually define that trend. That will help you to correct the size median. So this is not like that initial classification. It needs to be refined at least. So we start thinking about that, and we kind of look for like defining an acceptable threshold using something that we call percentile velocity trend. So what we define with a velocity trend is if we notice, let's make a little, let's make some of them. So we notice that you have velocity, you have some time. So when we define kind of like velocity trend, we want to think about this is not reasonable, so we want to get rid of this. So maybe you want to define a maximum and minimum between your velocities. So that could be like a filter that is associated more with the trends that you will find actually in a more geological sense, a more geophysical sense in your semblance. And saying, let's say, if I know that for in a run of time, let's say 0.5, all this upper tail, you don't want it to pass a filter, you will say, well, maybe velocity should be restricted between, I don't know, 150 up to 250 meters per second. And so you could start like defining like some lines that will tell you that velocity that is more representative. And therefore you could kind of like get rid of this tail, at least for the 0.5 seconds and so on. And the other one that we kind of like define is just a percentile. So in the past, like I mentioned, I use like this very rough binary classification, say whatever it's below or over 0.6, it's gonna pass. But as we notice, it passes this one, but doesn't pass too much of this. So when we have a percentile, this is just basically a number that describes the value of a given percentage within a minimum and maximum range of a vector. And that we can say, let's define like a vector that only have like 0 and 10. And if I tell you, well, which is the percentile of 50%, it's just a median, of course. But if we kind of like change the minimum, then it will change because it's gonna start like taking what is in the minimum maximum value and start like changing what is more representative of that. Another thing that you can do is just start adding more numbers, and it gets more representative of this. So let's get the median. So if you go for this, it will tell you that basically the median between all these 5 values between between 20 to 100 is just like 58. So it's just more representative of a range of values that you want to work on, and you say, well, this will pass a threshold. So that maybe will get us a softer, let's say, threshold, but then we kind of like use the velocity train to be a little more tougher with what is like an artifact compared to what is more like realistic. So for this, okay, so we define basically here a tolerance. So when we want to have a velocity trend, let's say we define a line and it's going to have a tolerance, a minimum and maximum. This is just basically to do that interpolation to create the line. And these two are basically the threshold, the minimum and the plus. You will notice with the tolerance, it's going to be just like 2 lines that will help us to divide like our data between a maximum and minimum, and then using the threshold, we could see what will pass the filtering. So basically NPS and NTS is just the size of the velocity and the size of the time. So what we say for the filtering, whichever semblance has the threshold that is below the maximum threshold that we assign with the velocity, and whatever is over that minimum threshold, we will save the pair of points. So we save the t pair and the x pair, which is just the velocity. You want to save those candidates and try to save those to create like the further filtering for your machine learning algorithm. So we do this, we notice. So basically, if you notice, this one is like the velocity trend that we defined. So this will be like the minimum threshold, and this will be the maximum threshold. And this is basically what happened with the percentiles. If we change this kind of like the value that we have in here, we will only change basically the shape of those lines. So if we notice, now our velocity spans like a little more closer, it's just moved to this. And now maybe the points that pass this filter are just gonna be different. Now let's go back to the previous one, but let's change the percentile. So we're using a very high percentage, 95 go between 0 to 100, and 95 is just like a large one. So if we decrease our percentile, it's just gonna make, it would allow more points to pass the filtering. So if we notice, keeping the initial one, but just like basically decreasing the percentile, a lot of more points will happen. So we will have basically more candidates to form that particular cluster. So we keep it in here, and it's more realistic that we have some trends, but it's still, now we actually get rid of the large tail that we found in the beginning associated with the semblance, that it's a little unreasonable, but we kind of like maximize the amount of points that will actually pass our threshold, but it's still within our velocity trends. So basically, these are going to be our candidates to eventually form the cluster that will help us to correct the gathers. And here's basically, we just concatenate the information that we have. So we save the t pair and the x pair is just the velocity one. We save those points and we gather all those together in just one vector that we define as st, which is an upper letter. Following, we have general functions to plot and to notice with more color the boundaries defined by some of our clustering algorithm that we are using so far. It's just k-means and Gaussian mixtures. So for the Gaussian mixture, and has a lot of like a Python scripting, which is sometimes confusing. But the important about this is that it puts some kind of like contours, and this is kind of reflected or associated more with the centroids. And the centroids for the Gaussian mixtures are going to be defined by how you name your cluster plus the mean. The means are going to be basically the centroids for this one. This is just basically just for plotting. We're not doing any calculations with this, so don't get too hung up on what is written in here. This one is, the following one is basically the one for the Gaussian mixtures. Here we use, and again, this is just functions to plot. Important about this that we use basically some kind of like the centroids, and for this in the k-means, in fact, the name that we define the cluster is just different. The labels is just cluster dot cluster underscore centers. So you will notice that depending which kind of cluster you're using, the way that the machine learner define of how they name the cluster center changes. In the k-means is cluster dot cluster centers, and in k-means in Gaussian mixtures, sorry, it's cluster dot means, and that will change depending on which kind of cluster you're using. So again, here, just for plotting, you're gonna see more like this. It's just decision boundaries. But the important right now is that when you start using the machine learning clustering to actually identify those. So let's go for k-means. One of the good things about k-means is actually already has been used already in the past in many times. But one of the downfalls that you need to know the amount of cluster, the number of clusters that you want to use. Let's say the points that you want to select, or the points that you want to start clustering your data. So that's a downfall, but since it's so well understood, we just went for that first. So here you just define with the k. K is just the number of cluster. Here you define like a random state, just so maybe all would you just get the same kind of random sequence, and you can use the algorithm full, or you can change it to, there's another one that you can use here. This one, the full one. And then you have the LCAN. It is also the other one, but the full one will just help you to just kind of like maximize just like an expectation, maximization, and I will explain a little more when I kind of like go and explain a little more about what k-means does. But let's run this and see what happens. So this is what we have for k-means. So basically we remember like these points were the ones that we passed to define those clusters. Well, using the k-means algorithm as it is, what we said is basically this large y dots with x's is going to be our cluster. But if we notice, it when define the cluster kind of horizontally, while saying basically it's kind of defining everything in velocity. It doesn't seem to have, if we notice, it put like this cluster within here, but it has some values in here, consider these values in here. So it seems that something is not entirely working properly within the clustering, and maybe it's not the clustering, but maybe it's more associated with a data set. So that's what we wanted to explore. So a summary about k-means is just, first of all, as mentioned, you specify the number of clusters you're gonna assign. Then you, and in our case, remember we're 10, but we can change that always. Then you could randomly initialize those centroids you're saying where you're gonna put those clusters initially. And then until it converges, it's just kind of like move those dots. Let's say I put some dots in here, and it will start moving those dots until it computes the means of the cluster and assign all the data points to the cluster points based on a distance of the, minimizing the Euclidean distance, which is just basically a Euclidean distance. And there is a problem associated with our data and the Euclidean distances. So if we think about like what it's doing, it's just x is basically a point. Mu is just the mean of the cluster. So each of them are gonna have some kind of information associated with the coordinates in x and the y axis. But if we notice our data set, in velocity, it at least it goes through 150 up to 350,000 meters per second. 1 second only spans between 0 up to 2.5 seconds. So if we notice, probably there's like a trend, there's a feature, let's say velocity, that's way larger compared to if we compare this in time. And maybe this is why when we notice this, it seems like the cluster everything's doing this based only on the velocity and it's not taking any consideration into the cluster that could be associated more with time, which is really important in our case because everything in our case, it's pretty much go together with velocity and time. So for that, to try to kind of see if we could not solve our data, but trying to make the velocity span within a range that is more like closer to the time, we kind of scale our data set. To do this, we use a standard scaler, and we basically just feed just kind of like transform, take all this information, make it like more similar in axes or in values. So if we notice here, we can already notice that it's working better. We're not changing anything within k-means. We're still using the same random state. We're still using the algorithm the same way, the same maximum iteration, the same number cluster, everything. But we only we standardize our data. So if we notice our data now seems to be spanning between similar values. And because of this, when it defined the cluster, it seemed to consider both time and a velocity information. So if we notice, we went for something linear, like until something that's, it seems that with the colors that you will start noticing that it has different shapes. And this is because it's associated the cluster, it's associating all these clusters in here in a time and velocity pair. And it's happening in both cases. So now it's not linear, only considered velocity, but it's taking consideration and time. Now we just go and take our information back to the original data space. And this is just to make a little comparison more next both of them. So this is the one that we noticed in the beginning without scaling. And this is basically the data set scale. And we went back again to go our cluster information and we scale here. We took the centroid information and we went back to our data space. So now we're basically just plotting the labels for our data set and just bringing that information back to our original data space and comparing what it looks like. So here we notice again that trend, the linear trend initially without any scale. And basically this is the one with after scaling and coming back again to your original data set, you could start noticing how it went from linear, you can see the velocity again, to a clustering consider both time and velocity. So the trend seems to be like more realistic in our case, and you can notice in some here, in this one in here. Now maybe to compare another clustering, we use Gaussian mixtures. So Gaussian mixture again has a little bit of downfall with k-means that you need to define the amount of cluster that you use. And there's something that you could define something named as a covariance. So we using this as full, which and that's when maybe after we run the cluster, just running the cluster. And again, these we're talking about the same data points. Now we're noticing where we put our clustering or our cluster centers. So if we notice without any scaling, we didn't have to do anything in particular, it kind of put those centroids more in a place that seems to be more realistic and taking into consideration both time and velocity without having to do any scaling. And maybe this is also associated with the covariance type. So for the Gaussian mixture, to do this, what the algorithm does is very similar to k-means, but basically it says that initial distance that k-means used to have the Euclidean distance, In our case, it changes, it uses more or less a statistical distance. And with statistic, we're talking about probabilities. And probabilities are drawn from Gaussians. And in this, this is basically the probability of X, which is a data point, given a cluster that you're, as you noticed, you're always going to define the number of your clusters. So given a cluster, what is the probability that this point is going to belong to that cluster? So in here we have, again, if you notice, this again seems to be the distance, but there's a very important character over here, which is just the covariance matrix. And in that covariance matrix, Gaussian mixtures allow to have some variance in your data, which doesn't allow to be, which K-mean doesn't be like allow when it's using like Euclidean distance. Because in the Euclidean distance, in fact, if we go back here, the Euclidean distance, it converts basically this covariance matrix in an identity matrix, meaning that it's gonna be 1, 0, 0. It's just gonna be a diagonal matrix that's gonna be only gonna have one in the main diagonal and zeros and the other. Therefore, the distance is basically this, given by this. Well, if we go and use the Gaussian mixture, it gives some freedom and it allows to have the data set, that variance over there. It doesn't give the same weight. It doesn't cluster everything in like in spheres. So that's why you don't have to scale, or at least you wouldn't have to scale your data set, even when it spans on different in velocity in in our case. You wouldn't have to use that in a Gaussian mixture because it uses a statistical distance. It will draw for the probability. So just simply as a k-means, it will draw from probabilities. It will start with some values and then will iterate until convergence. Basically, that's just to convert to have two different algorithms. And now what we try to do is just correct our CDP or gather based on information from the clusters to generate the NMO profile. So for this one, and we haven't done this so far, we just import the information associated with our gathers that is in ASCII file for like information of the auto, so we know which is gonna be like our OTIF in trace information. And we just basically load that information from seismic unit. We haven't done it so far, so. Basically, this is our original gather, get some hyperbolic events as expected, and that's what we want to correct with those center from the clusters. So what we try to do, just run here and create our CDP that these ones are gonna be the ones that are gonna be corrected. So basically this is the original one. Here we're gonna be the ones that are gonna be corrected, just creating that. And now we generate a NMO profile based on the central information. So here, since we're using both Gaussian and k-means, we're gonna sort that information because if we take this is just the information of the clusters. It's not organized, it's not sorted. So if we notice here, it's gonna have first, this is gonna be in velocities, this is gonna be in time. But if you notice the time, it doesn't have any order. So you want to have some order for that before starting to build your profile. And that's what we do in this one. This one in here, the minus one is just it's gonna order your data set based only on the time, but it will take the pair. So it will take the pair of, let's say, time and velocity, and it's gonna sort this list in both cases just on the information of the time. So using this, you will be able to have some sums of the velocity decrease, which could happen. This is just for sorting, and here we try to create a linear interpolation between those clusters just to create the velocity trend that we want to follow. And again, here just for k-means and Gaussian mixtures. And basically here we can see the difference between them. So basically here, if you notice, it allows to have like a negative value and it will work fine. If we notice k-means, the centers from k-means and Gaussian mixtures are not so similar. And this is, and even though we're using here the ones that were selected after the scaling, they are not exactly the same, especially on this part. On this and on the down tail seems to be very similar, but this one is not very similar. So we want to see maybe how that will work and see which one corrects the best in our case. So now basically we're gonna start doing the correction. So we basically we're gonna find the T0 on the time that we define in our velocity and CDC time. And then we're gonna span and we're gonna look at the value here and the velocity in the profile, and we're gonna correct these ones. One is for Gaussian mixture and the other one is for k-means, if you notice, you can see there. And if you notice, we went from this having those hyperbolic events to something that is really somehow kind of like flat, if you notice. I will say the Gaussian mixture in this case, since the k-mean seems to be a little bit better, especially for this event, seems to be better corrected. In this case, seems to be under corrected. So maybe there's something the velocity here that could be maybe the way that it defined the cluster, or the velocity trend. But it seems to be doing a little bit better with k-means. But originally, I think it solved our goal. It took all the information that we gave them, and it was able to correct our CDP gather. Now, something that I found very interesting, just Gaussian mixture in this case, and you can get more information on this one here, but you can change that covariance matrix, and we spoke about how k-means use the covariance matrix, but the covariance matrix is just an identity matrix. Look, what will happen if we use like a covariance matrix is just spherical, so each component has its own single variance. Seems to me that it's just another identity matrix. Look what happens. Well, it put the cluster and it seems to be really, really, really similar to the ones that we already, and I know the colors might be like all green and stuff, but if you notice where it put the centers, if you notice, had a lot of relationship with this one. So since you're using like the full one, it gets every cluster the opportunity, it has its own variance without you having to do all the scaling and stuff. And it gives you all that freedom, and it helps you maybe to adapt better your velocity profile. Although at the end, it seems like k-means with the scaling and they go back to your, one seems to be doing a better job. But that's something that could be discussed, and like there's other types of algorithm in which you wouldn't have to define the number of cluster, which is a little bit of downfall with k-means and Gaussian mixtures. And we're working on those currently, but at least it gives us a promising idea that using this idea without having to have much like an interpretive job, we can pretty much solve and kind of like correct our seismic information based on basically just mathematicals and algorithms. So well, that's basically all that we have so far. So if you have any questions.
Ninoska, thanks a lot for your presentation. I believe that this undercorrected velocity might be that point peaked around 1 second. If you go to the semblance peaked after this one, you have the k-means, you have that around 1 second, you have one peaked one cluster center that you don't have in the Gaussian mixture.
That's right, yeah.
Probably that's the one that made the best correction. Have you tried other covariance matrices besides spherical and full? What are the other options that you can have?
So yeah, we can play with this really quick in here. So you can have ties. So ties basically would allow some variance, but it will use the same variance matrix for all the clusters. So this is how it's gonna look. And we can run everything from here and see what happens. So basically this is how it becomes. So this we can just like simply run and see what happens. Let me just get to the final there.
I'm curious.
Yeah, I tried and I started playing with that. This is what happened. This is the Gaussian mixture. This is the correction that it does. And this is basically a comparison if you see the cluster.
Yeah, it didn't change much. Wow, that's nice that the k-means worked better.
Yeah, it works a little better.
And if you remove the first centroid, or the first centroid in time.
This one.
Yeah, if you just remove, maybe you can get. So there might be a way, for example, you could create a regression there. And this point is going to be very far from your regression line. So probably you can create a threshold like that, remove these kind of points.
Have you tried using different numbers of points as you're starting rather than 10?
Yes, and we can, everything's just really manual in here. So let me, if I change the K, it will change all of them. So we can change here. And you want it more or less?
Try both, try 15 and 5, just, I don't know.
Okay, so let's go try 15, just 5 first. Let me just find, go to.
Probably more would be better, I don't.
Yeah, probably, so let's see what happened in here. We're just doing everything. Okay, so this is basically the profile that generates from this. This is the correction that it does.
Yeah, it's always having trouble with that upper event.
Yeah.
So try 15, see if that helps it.
So one thing to keep in mind is that because it's a complex model, there's no guarantee that you will find a stacking velocity or make it flat.
Oh, okay.
So basically, yeah, that would be if we were working with a flat structure, we should make everything flat, but not necessarily in this structure.
You think the linear event is interfering at that point, Daniel?
Well, it's not basically to make everything perfectly flat. You have to apply migration, right?
Right.
So CDP is only an approximation for.
No, it still doesn't.
No.
Right. Yeah. Well, I mean, keep in mind that the CDP in complex structure doesn't have the meaning that is intended to, right? Because you don't really have energy coming all from the midpoint. The energy come all over the place. So that's why stacking is, for example, you cannot do time migration of Marmouze because of that. So you have to really.
That's really nice work, Ninoska. I'm really impressed. It's very nice.
That's amazing. I really love it.
So one point I want to make though is you're limited by the way they implemented k-means in scikit-learn. There's no reason you can't put the covariance matrix into k-means. I've done that, and you get virtually identical results out of k-means and GMM.
Right. Yes, I remember your paper from the. I think you were using Mahalanobis.
Well, which is the Gaussian, right?
Yeah, basically, yes.
And you know, I don't know why it is, but most books just assume you have to go with Euclidean distance in k-means, and you don't have to. So it's kind of like ingrained in people's heads. So we only use Euclidean in k-means. But I think in a book by Bishop, he calls the difference between the two the hard approach and the soft approach. I think the k-means is called the hard approach because it groups the data points after each iteration, whereas the EM algorithm doesn't. It just does it in a soft way. So, but theoretically, I don't see any reason why if you use the covariance matrix in both, you shouldn't come up with the same results, right?
Right, yes.
Maybe some differences, but I'm not sure.
Right, it's really restricted the way I don't know why they haven't implemented like that in scikit-learn. It's really, I don't understand. Like you can find another clusters that you can actually create like a pipeline and then kind of like work at that distance without having to change, like standardize your data set, but you cannot do that in k-means. I don't know why.
Okay. But it is, I was interested the way you were able to reduce the complexity of GMM back to being equivalent to k-means. So that was kind of neat, by forcing the things to be spherical.
Yeah. It's an interesting like problem, let's say, and we're trying now also with DBSCAN, which doesn't have like all this information. So we're only like trying to work more like with the density base, and it actually able to define more like points that are noise within your let's say your initial data points, and then from that kind of like defines the cluster center. So maybe not the cluster center, but it's something that they call like the core points that will be similar to the center of the cluster center. So that would be also nice to see how that adapts.
That's nice. Is it? So this is going to be your master's thesis, is that right?
No, this is probably just like a parallel work that we're working. It's interesting though.
It'll be a publication.
Publication, that's good.
Hopefully, yeah.
And just one question about the threshold that you choose for the zeros and ones.
Mm-hmm.
Maybe if you increase a little bit the threshold, you might have better separation of the points. You're going to have less points and probably more storage for the cluster. That might work better when you're going to try DBSCAN, for example.
Yeah. I mean, everything here is like manual. If we change, like the maximum it could be like 100, so we put in 95. So that's like, we can just restart all and see what happens. Supposed to. See what happens. I think I'm leaving only 50. See what.
Let's see. Yeah, you have less points.
I have, well, I left.
Oh yeah, but then you have to select 10.
Yeah, sorry.
No, but that's okay. Let's see how it was in the end there.
Yep, let's see how that goes. Wait. So here you have some. I still kind of have like this one on the top.
But do you even believe that trend at the top? Daniel, do you think that's real? Is that just some artifact that's coming in?
Yeah, okay, stop there, Ninoska, just a second there. You see in the top of the gather, basically you have energy just in a few traces. Okay? So the resolution you have there is very low. Basically, you just have a point there, it will map to all the velocities. So basically, you cannot do semblance at the very top. So I think we could just safely just remove.
Yeah, so I was saying if you remove them, maybe that would improve the solution.
Yeah. So basically, the point where you should start peaking is related to the velocity mute. Essentially, when you do NMO, right, you have a stretch mute. At a certain point, you don't have any energy. So if you are in the shallow, you should only have 2 or 3 traces. Right? We should, we could do that. We could just define do not start peaking before certain time.
That looks a bit better, actually.
Yeah, it looks better. Probably you could do like that. Every point that you can get the minimum velocity that you're going to have, and every point that has a higher velocity in a earlier time, you could remove something like that. Because the tendency that's the first peak is going to be the lowest velocity generally.
So was that a tighter threshold you suggested, Marcel?
Yeah, the tide.
So maybe by doing a tighter threshold, you removed more of that trend at the top.
Yeah.
Probably.
So if you go back to the velocity that you created there,
Let's go
the
back to it.
centroids in those cases. No. Oh yeah.
Up to the threshold, yeah.
Yeah, we still have a little bit of them. That plot that you have the two side by side.
Now I'm scrolling over.
Yeah,
You
we're
mean
almost
this?
there. Yeah.
No, I think it's scrolling down. When you have both centroids picked for the Gaussian mixtures and for the k-means.
Yeah.
After you do the linear connection between them.
The animal profile, you mean? After that.
Yeah.
Okay, so it's supposed to be over here. There.
Yeah, this one. Yeah, you still have a few artifacts, I would say, but I believe that you improved in that 1 second. You could improve a little bit the Gaussian mixture, for example. You have that centroid now because I believe that you created a better separation between the clusters by tying up a little bit the thresholds there.
Yeah,
So-
it's some.
Sorry, go on.
No, it's something to consider. We're still like working and see what it adapts better. So yeah, it's still like a work in progress, to be honest.
Good,
Yeah,
though.
the main thing here, we haven't, we start looking at that, but presented here is the multiple, right? So you have to be able to distinguish different trends for the primaries and multiples. That's the future.
And what about internal multiples? Could they put the centroid velocity a little down because of the
multiples are very difficult to distinguish with semblance because they could map on top of the main trend. I think it's very unlikely that semblance will give you a separation there. Surface multiples, yes.
Yeah, surface multiples show up better.
Yeah.
Okay.
I mean, it's possible. You can always try, but I think when you're dealing with internal multiple, you really have to look at the reflector that produces and to do a model and to figure it out. But
Okay. Does anybody else has other question? If not, I'm going to stop the recording, and I'd like to thank you everybody for coming and joining us today. So the next one in 15 days, we are not going to be presenting. You're going to be participating in a machine learning competition. So we're going to be a little busy to present. But in 1 month from now, or in 4 weeks from now, you're going to be start again with the Learning Lab 15. So thank you, and see you everybody soon.
Thanks, Ninoska. It's good.
Thank
Very
you.
good.
very good presentation.
Amazing presentation. Thanks a lot.
Yeah, very